On which aeronautical chart does a Rhumb line appear as a perfectly straight line? And on which chart does a great circle appear as a perfectly straight line? Two different charts, two very different answers. Confusing these two specific properties is the single most common cause of failure in the DGCA General Navigation Paper 1. To understand the answers, we have to look at the geometry problem cartographers face. The Earth is a three-dimensional sphere, but your navigation charts are two-dimensional flat surfaces. You physically cannot flatten a sphere without tearing and stretching the surface. Because of this physical reality, mathematical distortion is inevitable. No single flat chart can perfectly represent distance, area, and shape all at the same time. Since cartographers cannot eliminate distortion entirely, they have to choose which specific geometric properties to protect based on what the pilot needs. That choice creates the different chart projections. For the DGCA exams, there are three primary projection surfaces you need to know: the cylinder, the cone, and the flat plane. Wrapping a cylinder around the equator creates the Mercator projection. Placing a cone over the northern hemisphere creates the Lambert conformal conic projection. And projecting from a single pole onto a flat disk gives us the polar stereographic projection. Despite their distinct projection surfaces, all three of these charts share one universal property: they are conformal. On a conformal chart, intersecting angles are correctly represented. This means the shape of any landmass is mathematically correct on a local scale. However, protecting the shape comes at a severe cost to the scale. As you move across a conformal chart, the ratio between the chart distance and the actual Earth distance distorts wildly. Because all three charts share this identical conformal property, the examiners will never ask you to differentiate them by shape. They will test you strictly on how each chart distorts your navigation lines. We begin with the Mercator. As a cylindrical projection, it is mathematically optimized for equatorial and low-latitude regions. This map shows the strict rule of the Mercator. A Rhumb line is always represented by straight pencil lines, while a great circle will curve. The major drawback of the Mercator is that as you move away from the equator, the scale increases dramatically toward the poles. This scaling error is why Greenland appears to be the exact same size as the entire continent of Africa on a Mercator map, even though Africa is actually 14 times larger. If you are plotting a flight from Mumbai to Colombo, you want to fly a constant magnetic heading. That exact constant heading path is a Rhumb line. Because that specific route plots as a perfectly straight line on this chart, the Mercator is highly effective for low-latitude plotting. A straight line on the paper translates directly to a single, unchanging compass heading in the cockpit. Next is the Lambert conformal conic. This projection places a cone over the Earth, touching it at two specific standard parallels, which is where the scale distortion is at its absolute minimum. The geometry here inverts the Mercator rule. On a Lambert chart, the great circle appears as a nearly straight line, while the Rhumb line arcs into a curve. This nearly straight great circle property is exactly why the Lambert conformal conic is the official ICAO standard for global en route charts. These world aeronautical charts are universally published at a precise 1 to 1 million scale. It is the primary en route tool for mid-latitude navigation, meaning it covers the vast majority of Indian airspace you will be flying in.
The Lambert remains the global standard because presenting a great circle as a nearly straight line allows pilots to visually plan the physically shortest route between 2 points without performing complex mathematical conversions. Finally, we have the polar stereographic chart. This is an azimuthal projection, firing light from one pole onto a flat plane placed at the opposite pole. Its operational boundary is strictly defined. Navigators only pull this chart out for regions above 70 degrees north or south latitude. The ultimate rule for this projection is absolute. The great circle is an exactly, perfectly straight line. Near the poles, all the Earth's meridians converge sharply to a single point. Because of this extreme convergence, attempting to fly a constant compass heading is physically impractical. Since Rhumb lines are practically useless at the top and bottom of the world, following an exactly straight great circle is the only reliable method to navigate these extreme latitudes. Looking at the physical globe, a great circle is the shortest distance between 2 points, passing directly through Earth's center. A rhumb line, however, is a spiraling path, crossing every meridian at the exact same angle. This creates a strict operational trade-off. Great circles are physically shorter, but force the pilot to constantly adjust their heading. Rhumb lines cover a longer distance, but allow you to lock in a single heading for the entire leg. To understand the scale of this trade-off, consider a long-haul route. Flying a great circle from Delhi to London saves over an hour of fuel compared to tracking a rhumb line. This photograph of a navigator plotting illustrates the heavy manual workload required to manage these complex tracks. The only places where a great circle and rhumb line are exactly the same track are directly on the equator or flying precisely north-south. The reality of commercial aviation is that while pilots steer rhumb lines for cockpit simplicity, airlines plan great circles for maximum profit. This tension forces navigators to constantly convert between the two track types. To make that conversion, we define convergency as the exact angle between any two meridians at a specific given latitude. The core formula is convergency equals change in longitude multiplied by sine of mid-latitude. The conversion angle is exactly half that convergency. Add or subtract this angle from your great circle bearing to find your flyable rhumb line. Memorizing this single relationship, that the conversion angle equals the convergency divided by 2, guarantees passing marks on the navigation routing numerics. Urgent. Stop taking notes for a second and look at the screen. Here is your practice question. On a polar stereographic chart, do great circles appear straight or curved?